So our chapter on statistics, we're now down to just talking about the Grubbs test and reviewing our calibration curve information. So the tests that have been done so far that we've talked about, the F test, the confidence interval, and T tests, we're all about seeing if something was significantly different from each other in terms of the correct answer, like the known value in your data, or two sets of data. The Grubbs test is similar but different. So there are times when you're in the lab that you do multiple trials, and it could be that you did 4 trials, and 3 trials have very similar results. Your final answer, your calculated values were very similar, and one looks really off. So like significantly off to where you think something's wrong here. But we can't just throw away stuff. Especially in this course, you're not able to just erase things because you don't like them. That's not how this works. So the point of the Grubbs test is to determine if you have an outsider, like an outlier data point, the Grubbs test can determine if it's enough of an outlier that you can discard it. So it's statistically, again, following the Gaussian distribution statistics stuff, helps you determine if you can discard a data point because it's so different than the others. This is useful to you as a scientist in this course, because if you do your 3 trials and one of them is different than the others, the only way you can get rid of it is if you use the Grubbs test, and the Grubbs test shows you can discard it. So because what that would do is it'll significantly change your average and significantly change your standard deviation. So we're going to be using this, like, you're going to expect it to be tested over this, but in addition, you can use this at any point during the lab that you need to. Okay, so the Grubbs test. Here's the equation. We're going to be, just like with the F test and T test, calculating it's called the G value, the T calc, and we're going to compare it to the T table. And then based on those results, we'll determine if the data point can be discarded or not. So the equation is the absolute value of the questionable value. So the one data point that you're unsure of, minus the average divided by the standard deviation. And the average and the standard deviation are include that questionable value. Okay, so you're going to get your G calc out of that. And then you're going to compare it to the G value from the table. Okay, so there's the table that would always be given to you. So let's do an example. Here's my data points, and I want to know if the last data point can be discarded. Okay, so following the G equation for the Grubbs test, it's the data point that we're questioning minus the average over the standard deviation. Okay, so what I'm going to do is I'm going to save us some time and tell you I've already calculated the average of those data points. It's 12.54 grams. I'll tell you I already calculated the standard deviation, and it is 0.0804, okay, grams. I'm just trying to save us some time. So G calc. The questionable value is 12.67. The average value is 12.54. Oops, not 15.54. 12.54. And the standard deviation is 0.0804. So when I do this math, I get 1.59. Okay, is my G calc. What I need to do is compare that to the table value. So looking at this table, this column says number of observations. Notice it doesn't say degrees of freedom, but it's truly the number of measurements. So 1, 2, 3, 4, 5. 1.672 is the table value. So my calculated value is 1.59. So calc is less than table. So let's go back and look to see what that means. Well, if the calculated value is less than the table, the questionable point should be retained. So we cannot drop it. So we have to retain the data point. So we have to keep all 5. Okay. If the calculated value had been greater than the table, then the error is so big that we can drop that data point, and then that means you get to recalculate your average and your standard deviation, excluding that. So again, useful for tests and chapter 4 sapling, but also useful in the lab. So that takes us through our statistical tests. But to finish out this chapter, our calibration curves are all based on this Gaussian distribution statistical analysis stuff as well. So remember, calibration curves are graphical analysis comparing the response of a test to the known quantities of the analyte. So the known concentration. So that means we did our test using standard solutions, where we accurately made solutions with accurately known concentrations in whatever concentration unit you need, and then tested those with an instrument or a method, and then graphed the results of those tests on the y-axis and the concentration on the x-axis to get a straight line. So we're going to have blanks. So unless it's not correct, we're going to have a 0, 0 point to show when the concentration is 0 that the result of the test was 0. Now there are going to be some points, sometimes that's not true. There are some lovely internal standards and standard addition situations, but for the most part, we're going to have our blank, which will be our 0, 0 point. So it does not, and our blank solution should have everything that our normal standard solutions have, except for the one analyte. So there's one lab, this iron spectrophotometry lab, where you've got to add, I think it's 5 different chemicals together in the volumetric flask. We're only just measuring the iron ophenanthroline concentration, but we add all these other chemicals to it as well because they're necessary. So for the blank, we're going to add everything except for the iron. All the other chemicals are going to be there. So our blank needs to be exactly like the standards, just minus just the analyte. So we're going to make our solutions of our known concentrations and also our unknown. We will blank the instrument and then make our graph with the, I am going with absorbance for this example, on the y-axis and the concentration on the x-axis, find the best fit line using Excel, and then using the equation of that best fit line to calculate the response of the instrument, the absorbance, and that will be known from the data, and then use that value and our linear equation to calculate the concentration or the quantity of the analyte. Okay, so again, we're going to be doing calibration curves a lot. If you've got questions about them when it happens, let me know.